Okay, good morning. Enjoy the joke of the day. It's a good one. Hopefully you got it. Get it, oxygen. Oh, jeez. Okay, let's go over the homework. Hopefully you did it. Looks like this. Radiation could mutate you, giving you deformities. False. Usually, if you get enough mutation, if you get enough radiation, your cells will kill themselves. Like when you get a sunburn to the point where you start to peel. So you're not going to have deformities during your lifetime. Sleeping next to someone most nights for a year results in a radiation dose about the same as that for X-ray of your hand. That is true. All living things give off radiation. It's not harmful radiation. If you get enough X-ray radiation, it could be potentially bad for you. That's why they put that heavy lead thing on when you get your X-rays of your wherever, even in your teeth. You're supposed to cover everything up. Okay. Recent shipment of 1.5 tons of plutonium, and recent, remember this is 1995, so this is 25 years ago. Energy equivalent of 1,000 oil tankers. And I did some quick math on that. And the amount of energy in 1,000 oil tanker shipments is about 2.4 billion times less than the plutonium. So well, it's pound for pound, I should say, pound for pound. So this is true. So you only need 1.5 tons of this, and 1,000 oil tankers. Each one of them carries 86 million gallons. 86 million times 1,000 is 86 billion. 86 billion gallons of oil. Some TVs and computer screens emit radiation that can cause cancer. That's true. Most of those TVs are gone, the old ones, using cathode ray tubes. They don't make those anymore. Now LCDs and LEDs, they don't give off much radiation at all. Many dentures are radioactive. Well, when this was made, that was also true. They've gotten away from that, but some still probably have some radioactive parts in them, the porcelain in them. Irradiation of strawberries to retard spoilage, to stop spoilage, causes strawberries to be slightly radioactive. That is false. The radiation goes right through, and the purpose of the radiation is to kill any fungus, bacteria, or viruses that might be on there. So it doesn't leave any radioactivity in the vegetables at all, or meat for that matter. Living 1 mile from Chernobyl during the accident would be more likely. You'd be more likely to cause your early death than being 5 pounds overweight. That's true. In 1986 is when the Chernobyl nuclear reactor exploded, giving off a large amount of nuclear waste. I shouldn't say nuclear waste, of radioactive waste from that area, which was in the Ukraine, which is kind of south of Russia. And there were some problems with that. Everybody moved out of there. Organically grown tomatoes are not radioactive. That's false. Everything that is living has some sort of radioactive emission. Radioactive waste with a half-life of 1 trillion years is more dangerous and difficult to store or dispose of than is otherwise a half-life of 24,000 years. Well, it's partially true, because if it has a half-life of 1 trillion years, you're going to have to, the container that you've got is going to be much more challenging than if it's 24,000. This is going to be challenging anyway. So you're going to have to, in either case, you're going to have to make sure that the storage containers can withstand the years of the radiation coming out. Chernobyl accident has resulted in deformed animals being born. That is true. Not the animals that were there at that time, but the offspring of them. Take that back here, hold on. I think I've got a picture or two. I don't think this is the right page. I don't think that is either. So that's a little graphic. This is, I don't know what year this was. This is updated, but that picture is from a while ago. You can see the mutations there from the calf. So the amount of radiation that was that the animals were exposed to gets transferred. It alters their sperm and eggs, and then you've got the mutations that end up with deformities in the offspring. Transportation of fruit and vegetables will cause more death. Yeah. Transportation of nuclear waste, you don't really see that on the highways because they do a good job of hiding it. But that's true. More people are going to die in car accidents and truck accidents from fruits and vegetables. A pound of plutonium dust dispersed over a city would cause over 100,000 deaths. That's false. There would be some radiation involved, but not enough to cause 100,000 deaths, or maybe even one death. The 3 Mile Island nuclear reactor will ultimately result in over 1,000 people dying of cancer. That's also false. 3 Mile Island was the first nuclear reactor accident, and that was in 1979. Not a lot of radiation got out there. So, all right, see what you did with that one. All right, we are going to learn about beta and gamma radiation right now. For those 1 or 2 people who are actually watching these videos, I can see how many views there are. The last couple, 0. I don't know how you're getting the information. I have a feeling that it's a giant borrow fest out there. But anyway, yesterday the video, if you watched it, you filled in notes about early scientists like Marie Curie and her husband Pierre and Henri Becquerel. And then we learned about alpha particles, which are kind of the biggest ones. And when that happens, if an element gives off an alpha particle, it's the same thing really as giving off a helium particle, helium atom. And what happens is that they become lighter. It turns into a different atom altogether. And the reason why it would do that is because it's unstable. Remember, any element above atomic number 83 is going to be radioactive because there's not enough glue, quote unquote, to keep it all together. Okay? So we got down through here. These are alpha particles, could potentially do a lot of damage, but because they're so big, they can't penetrate much of anything. So even a piece of paper would be able to stop alpha particles. All right. Today we're going to learn about beta particles and then gamma rays. Beta particles produce when a neutron is converted into a proton. Neutron into a proton. So in this case, what happens is, because of the instability of the nucleus, a neutron is going to eventually get converted into a proton, resulting in an electron coming off of there as well, and something called an antineutrino, which is not anything we're going to learn about. Okay? So the increase in charge of the nucleus also kicks out an electron, which might make sense to you. If I convert a neutron into a proton, now I have more protons than I did over here, and as a result, could end up kicking out even more particles to make it more stable. Beta particles are actually high-speed electrons. They have a certain symbol that you should be familiar with. Let me show you on your CRT. It's in table O, which is here. We looked at alpha particles yesterday. Helium atom, you might see it as a Greek A. These are beta particles. They're shown with an E because it's really a high-speed electron with a -1 charge but 0 mass. You might see it shown like that. They have a charge of a -1, just like other electrons. They have a mass of 0 AMU. And they have intermediate, kind of in between, intermediate penetrating power. And instead of being stopped by a sheet of paper, they could be stopped by a sheet of aluminum foil. Okay, so aluminum foil is pretty thin, but it's still thick enough to be able to stop these things. Okay, so beta decay results in a change in the atomic number since a proton is made. Since a proton is made, the atomic number is going to increase. So these are the types of problems you should be able to work through once we are done with this section. So let's see how this works. Over here is shown the beta particle each time. Here is the element that is radioactive that is giving off the beta particle, but it's going to end up with a different product here. So what's happening here? Helium, let's start with uranium. Uranium is 92 atomic number, and it gains a proton. So in order to figure these out, all you really have to do is take this number and then add it to whatever's left over. We're looking at beta particles today, but in alpha particles it's the same thing. So in this case, whatever the total is here, 93 and -1, has to equal 92. 235 is not going to change because there's no change up here. So my top number is not going to change, so that's going to be a 6. So what number is going to end up making 2 if I've got a -1 here? So 3 plus a -1 is 2. So what element has an atomic number of 3? That's lithium. Okay? And this is an isotope of the most stable one, of lithium-7,3. I shouldn't say most stable, most common. Okay, iron 26. So the number up here is going to be 52 again. And instead of 26, this is going to be 27 because a neutron gets converted into a proton. So 27 and -1 is 26. So what's 27? What's that, cobalt? 27 is cobalt, yes. Okay, so we're changing, this is an actual change in element. All right? So beta particles have medium ionization power as well. So both of those are intermediate. Intermediate, in other words, they can cause some ionization, which in terms of safety is basically what kind of damage can be done. But beta particles, not too much damage. You're more likely to get damage from alpha particles, but since they can't penetrate very much, then it's usually not a problem. Okay? And the last little bit for today is gamma radiation. Unlike alpha and beta particles, that's a P, particles, gamma radiation is just a range of very short waves of energy. So I described this yesterday. The shorter the wavelength, the higher the energy. So gamma rays are way over here, very small. Radio waves can be hundreds of meters long, 300 feet long. And these are very small. And we can only see within this range. Okay, Roy G. Biv. So gamma radiation can be potentially dangerous. It has this symbol. Let's look what it looks like here. We have gamma radiation here, 0, 0. It looks like a Y, but it's a Greek G. It has no charge and no mass. It's just energy. It's really similar to high energy X-rays, and they have high energy, or excuse me, penetrating power. If we're comparing, we'll put higher. Higher penetrating power, it would take several centimeters of lead, Pb, to stop them. The atomic mass and the atomic number remain the same because this isn't a particle here. There's no charge and no mass. The energy content of the nucleus increases though. Decreases because it's being emitted. So you end up with lower energy products. Okay? Usually emitted with other forms of radiation. So here's your gamma. And by now, hopefully you recognize that that is the same thing as an alpha particle. So how would I figure out what uranium-92 decays into? Well, I don't have to worry about this because it's just energy, but I have to account for this. So 238 and 4, that's 234. And 92 and 2, 90 plus 2 is 92. So this is 90, I think, is thorium. Let me make sure. 90 is thorium, yes. Okay, so this is both gamma and alpha decay. During this alpha decay, gamma radiation comes off. All right, so let's look at your homework. Nope. Let's try it again. This one, it's in the packet that got sent home. This is the same as the bottom, so all you have to do is these 5. Take a look here though. Whoops. Use table N to look up the decay mode. Let's look at that for a second. Here's table N. So this tells me what the nuclide is. This is the radioactive one. How long it takes, and we'll learn about that in the next couple of days. How long does it take for half of it to decay? And then this is the decay mode. This is a beta. This is a positron, which we'll learn about tomorrow. There's an alpha. Okay, so those are really the 3. So you know that this is an alpha. That means that francium gives off a helium atom for 2. And then you can use that information to figure out what happens here with potassium. Okay, so try that out. We'll go over it tomorrow. Anything else? All right. Watch this. Ooh, sideways.